Chapter 12, Static Equilibrium. In this chapter, we study a special case of what's called static equilibrium. In the previous chapters, we spent a lot of time studying what happens if an object undergoes linear acceleration and then angular acceleration. But there is a special case which is of great importance. For example, when you build a bridge, you don't want the bridge to move at all. You want to be simply stationary. You want to be there, not moving at all. That, of course, is a static case. And how do you ensure the bridge is not moving anywhere? Well, you want to be in what's called mechanical equilibrium so that it doesn't move or doesn't rotate. So what is static equilibrium? Well, it is a special case of mechanical equilibrium in which the object does not have any acceleration. Static means not only does it have no acceleration, but in fact the velocity is also equal to zero, so that it simply stays there. As we know, in many cases of practical importance, when you build a bridge, a building, whatever, that of course is an important special case. Now let's look at what it takes for an object to be in static equilibrium. Well, first of all, since it is not moving, you know the center of mass cannot have any acceleration, right? What does it take for the center of mass to have an acceleration? Well, as we learned, we must have a net force if we want the center of mass to have an acceleration. And since we don't want the center of mass to have an acceleration, what is the net force equal to? That would be zero. Okay, so that's the first condition. No acceleration, or precisely no linear acceleration. The center of mass cannot move, and therefore the net external force would have to be zero. And secondly, it is also possible that even if the center of mass is not moving, the object can still rotate with an angular acceleration about the center of mass or about any other point. We don't want this to happen either, and therefore we also want to make sure that there is no angular acceleration, so the net torque is also equal to zero. Okay, so this is a pair of conditions which guarantees the object to be in static equilibrium. The first condition says the center of mass doesn't have an linear acceleration. The second condition says you cannot rotate with an angular acceleration either. Okay, so that is the condition for static equilibrium. Let's take a look at the second condition. The first condition is obvious. There's no, there's no external force. Just add the forces up. They have to be zero. When you study torque, we learned before that torque equals lever arm cross force. And the lever arm, of course, is measured from a given observation point. So the question is, which point do we use? Does it make any difference if I choose a point A and point B to serve as the observation point for me to calculate the torque? Will this formula give me different results? Well, let's see. So now the question is, which observation point should I use to calculate the torque? Okay, now suppose I have this object, right? I have 2 points, point O and O prime. This object is in static equilibrium, which means any point, including O and O prime, are basically at rest. They're not moving at all. And I consider a force F1. That's one of the many forces exerted on this object. How does one calculate the torque provided by this force F1 from the perspective of point O? Well, you know what I have to do is I need to draw a vector, in this case this green vector, starting from the point of interest point O, extending to any point along the line of action of F1, so I get R1. Okay, then I figure out the torque exerted by F1 about point O. That is torque tau 1 equals R1 cross F1. That's the definition of the torque. On the other hand, I can also calculate the torque provided by the same force F1 about a different point called O prime. What is the vector leading from O prime to a point on the line of action of F1? Well, suppose the vector connecting O and O prime is R1 prime, then obviously from this vector triangle, you know R1 minus R1 prime would be this black vector which I'm looking for. Okay, so tau 1 prime, which is the torque exerted by the force F1 relative to point O prime, would be this lever arm, which is R1 minus R1 prime, cross F1, right? Okay, let's work it out. The first term is R1 cross F1. The second term is R1 prime cross F1. You notice that R1 cross F1 is just torque 1, right? That is the torque of the same force from point O. So that's torque 1. The second one is minus R1 prime cross F1. Okay, this is the torque provided by F1 from a different point O prime. Now we know that due to the equilibrium condition, the torque exerted by all the forces about this point O has to be 0. So you sum over all the torques about point O, you should get 0. Those forces include F1, F2, F3, and so on. If that is the case, my question is, what about the torque exerted by all these forces about point O prime? Now we know that has to be 0 as well, otherwise it's going to rotate about O prime with an angular acceleration, right? But once we know for sure that the force is, the torque is 0 about point O, do we still have to make sure specifically that the torque is 0 about O prime? Or is it possible that once the torque is 0 about this point, it is also 0 about all these other points like O prime, so I don't have to worry about other points? Well, let's see. Again, let's write down the expression for tau prime. We know tau 1 prime equals, I'm just copying it from the previous expression, tau 1 cross R1 prime, minus R1 prime cross F1, right? Now, this is only one torque, of course, provided by F1. Let me add all the torques up, okay, from all the forces. So I'm adding it up. So this is not just tau 1 anymore, torque I, okay, summing over I. So I'm summing over I now, and I'm going to sum over I here as well, I and I. Now, take a good look. What is this equal to? This is the sum of torque over all the forces about point O, and that, of course, is 0. Look at the second term. In the second term, we have R(I) prime cross, this is R1 prime, okay? If you take a look at this expression here. Okay, if we take a look at this diagram again, R1 prime is actually a fixed vector going from O to O prime. Okay, it has nothing to do with the index I. I mean, I didn't really need to use this index I, because even if I change to a force to F2, F3, F4, this vector going from O to O prime is still the same. So it's a constant vector, okay? It has nothing to do with the sum, so I didn't have to use R(I) prime, just use R1 prime. It's a constant vector. So what I'm going to do is I'm going to take this vector out of the summation. So the second term becomes R1 prime cross the sum over all the forces. Okay, basically what I did, I took this term out. And what is this equal to? Well, that's the sum over all the forces, and by the first condition of equilibrium, we know this has to be equal to 0. So you see, the right-hand side of the equation, you have 0 plus 0, so that is 0. In other words, as long as the torque about point O is 0, and as long as the net force for the whole object is 0, then the torque about any other point O prime is also equal to 0. Okay, let me write this down specifically. What does that tell you? It tells you that you can choose any point. You can choose any point in the system to calculate the torque. And if that torque equals 0, that guarantees that the torque about any other point is equal to 0 as well. Why do we emphasize on that? Because that gives us great flexibility. Okay, here's the key word, flexibility, in choosing the observation point. Because even though all these points, when you calculate torque, you should give the same result, right? If the torque is 0 about one point, it's got to be 0 about any other points. That's guaranteed from the analysis we just made. They may not have the same degree of difficulty. It is possible for us to choose a point wisely so that about that particular point, the calculation becomes much simpler. And you will see plenty of examples. But make sure that you realize that you have the freedom or the flexibility to choose any point to apply the torque theorem because they're all equivalent to each other. Okay, before we look at some examples, let's first look at a very important special force, and that is the force of gravity. If I look at an extended object, every part of this object contains mass, therefore it contains weight. Let's say, for example, this object, we use representative points for this object. You've got point 1, 2, 3, 4, and so forth. Every point has its own weight, a little bit of weight, and they could be different. We learned that as far as the center of mass is concerned, you can think of the entire force exerted on an extended object as if it were a single force concentrated at the center of mass. As far as the center of mass acts linear acceleration is concerned. Okay, but that analysis of condensing the entire object into a single point is more or less limited to linear motion because it has to do with, the linear acceleration of the center of mass. What about rotation? Is it possible that when I look at the effect of gravity on an extended object, as far as the torque provided by gravity, is it possible for me to imagine that all these little forces spread out through the object, little gravitational force, is equivalent to a single force exerted on a single point called the center of gravity? Will that equivalence yield the same net torque, not just the net force? Okay, as far as the net force, you just add all these forces together, right? So this mg, that m, is the total mass of the entire object, times g, of course. That's the sum of all these little forces. But what about the torque? Will this force exerted on the single point called the center of gravity yield the net torque of all these little forces spread throughout the entire object? If we can do that, then things will be much easier for us because we no longer have to worry about an extended mass distribution or weight distribution anymore. When it comes to torque provided by gravity, let's imagine that the entire weight of the object is concentrated on one point, and through that point there is a force, and the torque of that force is the net torque of the gravitational force on the entire object. Can this be done? Well, let's see now. Suppose I have this object. Okay, I have this object. And I'm going to use a point, any arbitrary point, point O, as observation point. Now, and let's look at all these little guys. These are representative points on that object, each containing a mass, therefore a weight. Okay, let's look at this particular mass. Okay, there is a mass, of course, so it's got a weight. This is the ith object, ith part of the object, and therefore the mass is called m sub I, okay, and the weight, of course, m sub I times g. How much torque does this little force provide about point O? Well, I need to find the lever arm, and there we go. Here's the lever arm extending from the point of interest, the observation point, perpendicularly to the line of action. Okay, here's the line of action, right? And that's r sub I. Okay, and it's already perpendicular to that force. So, as far as the torque of this little force is concerned about point O, all I need to do is simply take the product of Ri, Mig. So, tau I equals Mi G Ri. This is just the magnitude. As far as the direction, it actually is, it promotes a clockwise rotation. Right? This is the torque by this little guy. Of course, here you have an entirely extended object. Therefore, I must sum over all the forces, all the torques, that is. So it's sum over I. So the torque of the gravitational force equals to the sum over all these torques. And that is sum Mi Ri G. Right? G is a constant. Let me take that G out. Now, does this look familiar? mi times ri? Well, you recall, this is related to the definition of the center of mass. As a matter of fact, if I divide this by the total mass of the object, and then I multiply this by the total mass of the object, what do I get here? Isn't this the position of the center of mass measured from point O? Okay? So I can write this as mg RCM, right? This is by definition the position of the center of mass, and let's say RCM is located at this distance. This is RCM, after your calculation, RCM. Okay, then you see, I can replace all these extended forces by a single force right here, which is equal to mg, see, mg here, and the lever arm of that force is RCM, see, RCM, and that takes care of all the torques summed together, which is the gravitational torque, the net gravitational torque. So indeed, it is possible for me to find a single point, and I can pretend that all these external extended gravitational forces throughout the entire object is concentrated on this one point. Not only does that give you the total gravitational force, but also gives you the same amount gravitational torque, because you see all the torque summed together equals the total gravitational force times the lever arm through about that particular point, and that particular point is no other than the center of mass. Now, it is not only called the center of mass anymore, we also call it the center of gravity, because again, gravity is equivalently exerted on a single point here. So this is Cm, and it is also Cg. So with that in mind, when we look at static equilibrium of an extended point, object, which often deals with gravity, of course, we can just, whenever we see gravity, we just find the center of mass, which is also the center of gravity, and we draw the entire weight of that force through that single point, center of gravity. We can